Hello, friends. Welcome to another lecture. In today's lecture, I will tell you one of the great topic, one of the great mysteries in all of the cosmos and all of the astrophysics, which is in the news nowadays about the black holes. The black holes are very astonishing objects in our cosmos, and it really the astronomers have done great jobs regarding to understanding black holes. To understand the black hole, you have to be well aware about the escape velocity, the basic idea what the escape velocity means. And let me give you an example. Escape velocity, the idea of escape velocity came from Isaac Newton. When you imagine a situation that you are standing in a mountain and you have a cannonball, and that cannonball you are firing, suppose object, rocks, and in such a speed you fire a stone that it does not come to the earth, and instead of falling into the earth it makes an orbit around the earth. then he then he conclude that that speed which you need to shoot a rock, to shoot a stone, to from that it will cross the gravitational field of the earth, and he gave this name that it is known as the escape velocity. Escape velocity is related to the gravitational field. Every object, every mass has a gravitational field, and associated with that gravitational field, if a object needs to cross the gravitational field, then it need a speed. From that speed, it can cross the gravitational barrier of that object. And for the earth, this escape velocity is a fixed value, and every object has its value is 1.2 meter per second for earth. But how this escape velocity give the idea of a black hole? A escape velocity, the black holes are those things in our universe that even the light, which is the fastest object in the special according to a special theory of relativity which Einstein proposed in 1905, that the escape velocity in the black hole, the light cannot escape through it. From there, the speed, the escape velocity of the black holes are very very large. And the Newtonian gravity, let me tell you about the gravity somehow, because gravity is related to the black holes. The Newtonian gravity we are very familiar with, and it is being taught in our high school physics textbook. It was defined with associated with two masses. If you have two masses, then they both exert a force. That force, what we called that this is the gravitational force between these two objects. Newtonian gravity is the weakest gravity, and Newtonian in the very high strong gravity regimes, the Newtonian gravity will break. If you apply those in the Newtonian gravity in a very high strong gravitational field, then as equation become to break down. And Newton also told us that mass and energy are two different things. But when you look at the general theory of relativity, which is the beautiful theory of gravity which was proposed by Albert Einstein, then he he explained mass and energy in a different way. But according to Newtonian gravity, mass and energy are two different things, and they are not related with one and another. William Herschel discovered planet Uranus by an accident. Now we apply Newton gravity to trace the object of the in our solar system. We apply it to Uranus, and we see that it is showing some deviation, and astronomers became confused at where this deviation is coming from. They thought that maybe there is another planet which gravity is tugging on this planet. Due to this, it is showing some deviation, and we have not conclude include that gravitational force of that planet in our calculation. Now let's do the math and find that is there a gravitation, is there a planet due to that planet Uranus is showing some deviation, and they calculated and they find a planet Neptune that due to the Neptune the Uranus was showing some deviation. And now we are tracing the orbit of the planet, and we came to Earth, Mars, then we came to Venus and Mercury, and here we see that Mercury is showing some deviation again. Why? Because Mercury is the closest planet to the sun, and sun has a very gravity, a very strong gravity. And here when we apply Newton's gravity the laws, then his equation becomes to break down. Then from there we need a strong, we need another gravity, the theory of gravity. Then Albert Einstein came into the picture. It was a small introduction about the Newtonian gravity. Now the fathers of black holes, the two of the astronomers, the great minds in the field of physics worked on these objects, Albert Einstein and Stephen Hawking. Now come to the Einstein universe. Einstein in 1916, Einstein proposed a theory which is known as general theory of relativity. It is the most beautiful theory in all of the physics which explain gravity in a different way that Newton has done before. And according to a special theory of relativity, mass and energy are the same things by a equation E equal to mc square, which was proposed by Albert Einstein. A special general theory of relativity explain gravity in a new perspective. According to general theory of relativity, mass and energy warp the fabric of space-time. It is you can see it from this picture that the sun is warped its surrounding, and the general theory of relativity said that the mass and energy when they combine together, then they warp the fabric of space-time, and every planet then orbit the sun. And it was the basic idea of general theory of relativity. And general theory of relativity is the theory of the strong gravitational field. We astronomers, we physicists apply general theory of relativity in very high strong gravitational regimes like black holes, neutron stars, pulsars, and these objects. And in general theory of relativity, we find something that the rate of time also will depend upon the gravitational field. If there is a very high gravitational field, then your time will slow, it will run very slow rather than a weak gravitational field. And it was shown by general theory of relativity. And from this slide you can get a very clear understanding of the black hole. Suppose this is the sun and you squeezed the size of the sun, and you see that the fabric of space time is being squeezed by this mass. And if you squeeze this sun in a size of this earth, and then that sun become a black hole. Why? Because you are decreasing its mass. When you decrease its mass, and its radius is going to be decrease, then when its radius will decrease, then the escape velocity which the light required to cross the gravitational field of a black hole is not sufficient, and then the light is trapped into an object which is known as the black hole. Now come to the properties of black hole. Black hole are real, and we discovered them, we physicists discovered them, not science fiction movies. The properties of black hole have certain properties. They have mass, they do spin, they have angular momentum, and their angular momentum is conserved, and the rate of time runs slower in a black hole than here in earth. And there are three types of black holes: stellar massive black holes, and these black holes produce they came into existence when when a star will end its life with a big tremendous amount of collision, which is known as the supernova. When its end, supernova is the last stage of a star life. When they burst in a supernova explosion, then the final object will come into existence, that is a black hole or neutron star, depending upon the mass of that star. And stellar massive black holes range from 300 solar masses to 100 solar masses. On the other hand, the second type of black hole is intermediate black holes, and their masses range to 100 to 10,000 solar masses. And the supermassive black hole, and their mass is range to 15 billions or 15 billions to 100 billion solar masses. And supermassive black holes are present in every center of the galaxy. We have a In our galaxy Milky Way, we have a supermassive black hole which is known as Sirius A, and Andromeda is also one, and every galaxy is a black hole. Now, are black hole reals? Aren't there fictions? No. The answer is no. Black holes are real, and in last time we have discovered a black hole by 8 event horizon telescope, and we move these event horizon telescope on the towards the sky, and we find a black hole that is M87. And we physicists have a strong claims that every galaxy contain a black hole, and due to that black hole, every galaxy is spinning. Black hole are real. And LIGO LIGO experiment is also shown us that the black holes are real. LIGO experiment is done a great job, especially in understanding of the nature of the black holes and the existence of the black hole. Yes, they are real and they are present in our own universe. When waves was discovered by the LIGO team, by the collaborations of many engineers and physicists, when they received these waves in 2017, and Kip Thorne got the Nobel Prize for this discovery, what they find something interesting. They find that when these gravitational waves are being produced in the fabric of a space-time, if you throw a stone on the pond, then you see these water waves are being produced. Then in the same way, the gravitational waves are also same as the water waves, but they are being produced due to two black holes, the collision of two black holes or neutron star. When these black holes spin, and their gravitational field will make them to collide one another, then they collide and become one black hole, and then they produce the beautiful patterns, and those patterns are known as gravitational waves. And LIGO has detected those gravitational waves, and conclude that black holes are real. And Kip Thorne also got Nobel Prize in 2017 for this discovery. It opened new windows for the field of black holes, especially for understanding the nature of the black holes. And now let's come to Hawking's universe. Stephen Hawking did something very interesting. He thought that from the name of black hole, many people judge that black hole are black, they do not radiate. But he, in the quantum level, he understand that black hole are not actually black, they are radiating energy. He apply Heisenberg uncertainty principle. Imagine in a vacuum of a space where there are particles, and the particles are in pair which are known as virtual particle pairs, and every particle is an antiparticle. A electron is an antiparticle which is known as positron, and every particle is a antiparticle. When these particle and antiparticle became one, then they are known as virtual particle pairs. And imagine that in the event horizon of a black hole, if there is a virtual particle pairs, then one particle will escape and the other one will go into the black hole. And when that particle, that impelling particle go into the black hole, into the singularity of the black hole, and that which escape from this event horizon and came out of it, then that is known as arcing radiation. And he conclude that from there, we in the quantum level, we understand that black hole are not actually black, but they are producing energy, and that radiation is known as arcing radiation. Now, what happens inside black holes? We know that black holes have a singularity from where density is infinitely high. When the word infinitely comes into the picture, then it's mean we don't know. We do not do any physics on the singularity basis of the black hole, and from there our equations become to break down. And what happens inside the black holes, we still don't know. We don't know what if you throw a information, then what happens to it. We have no any idea. If you throw a equation of the physics into the singularity of the black hole, then we do not have any idea what this information is going to be destroyed forever or it come back to another shape. We don't know. And in the singularity, the density and the mass and the concentration of mass and energy is so high, infinitely high, that we do not do any physics on it, and from there our equation become to break down. What happens if, according to arcing radiation, if the black holes are evaporating, it means that they are emitting energy. If they are radiating energy, then what at the end of their life be? Will they evaporate and disappear? We have no any idea. But but we are not still done from here. We have a string theory, which is the most theory all of the physics, which try to define, combine general theory of relativity, the theory of very big, and the quantum theory, which is the theory of very small, to combine those into a unified theory, which is known as the string theory. But we because we do not have quantum gravity, due to this quantum gravity, we do not still know the what happens at the singularity of the black hole. And we are doing so many research on this, and we hope that one day we will be able to answer these questions about the black hole. It was a topic, a brief introduction about the black holes, and I hope you got something from this lecture. Thank you for enjoying. If you have any kind of question, then try to comments me if you want.